Looks like not everybody's too blurry-eyed. Thank you for joining me early this morning. And so I want to share with you some preliminary work that I'm doing with one of my PhD students on trying to quantify what's going on with the strength of edges. And we're going to kind of bring a new twist to it a little bit and look at it from a little bit different point of view with this. And so I'm just going to walk you through what is our motivation. So right now, ASTM E1300 is based solely on infill panels, and it just addresses the strength of the surface of the glass. And there's several spots throughout the standard where when we start putting the edges in significant stress, the standard becomes, it just doesn't address those issues, okay? So when you start having partially supported edges or unsupported edges, the standard kind of starts hand-waving a little bit. And what I'm trying to do is get to where we can quantify the strength of the edges in a meaningful way in line with the philosophy of the glass failure prediction model the standard uses. So we can start addressing things like structural uses of glass, or at least having these edges that are going to be loaded more than they would be in an infill panel. And have a nice winter picture there of Michigan Tech through the glass, and we have a lot of snow there. And so just a brief recap. Remember, with E1300, we're basing the strength on this idea of having surface flaws that get, when put in tension, kind of grow or expand and sharpen, thus creating a stress concentration. And at some point, that becomes a critical stress that actually initiates fracture. And so we want to try to extend that kind of philosophy onto what's going on with the edges as well, because we have flaws in the edges too, from cutting, polishing, and just whatever we're doing to the edges beyond just cutting. So I want to give you some nomenclature of what we're talking about, because this is going to become important as we move forward. Is that I'm going to have, so we've talked about, we know what the surface is. That's just going to be the plane of the glass. And then I want to distinguish between what is the edge face and these edge lines, actual corners of the edge, the interface between the edge face and the surface. And that's what we want to focus on in our research here. And the idea here is that if we understand what's going on not only with the edge face, but also with the edge lines, then we can start building a risk model, or a glass failure prediction model to extend to address whenever we put those into tension. And because there's so many different treatments of edges otherwise, we really want to try to distinguish what is going on with the face and going on the corner. So how are we going to do that? Okay. So before I go into that, I want to show you what are we going to modify in this glass failure prediction model in order to be able to account for this. So remember, we said that E1300 currently just addresses the surface. We have this probably a breakage limit of 8 in 1,000, which we're going to consider more of just like a statistical artifact that we use for the standards, but again, only for the surface, okay? So the way that works is that the glass failure prediction model is principally based on a Weibull distribution, and the key thing that we need to recognize is that the material or the risk function that is used in the glass failure prediction model is different than the base one that is part of Weibull distribution. We've added some pieces in there to account for area effects, okay? And this is why the glass failure prediction model is nice, because we're not looking for just a single largest stress. We're not assuming that the glass is going to fail at the location of the single largest stress. The glass could actually, that critical flaw could be somewhere other than that maximum stress. And so because we're taking into account the area, we can address that with those. And so what we need to do is modify this. And so based on work that was advanced years ago by Walker and Muir, we can, instead of taking it with respect to the area, we can take it with respect to a length, or in this case, the length of our edge, okay? And what's nice about this is that once we kind of normalize this, or taking the length effect out of the edge, then we can start applying this however long the edge is. Okay, that's going to be a key thing as we move forward. So how have we been doing 4-point bending tests? Either we do it like 1288 specifies, where you're typically taking a standard sample size and you're loading it as in the top, kind of with the flat, flat side. But we can also turn on its end and do a standing test or this vertical. And in both of those cases, we're exciting. In fact, the first 4-point bending test is intended for the fracture to happen in the field of the sample. It's not intended to happen at the edges. And the problem with the vertical one is that we've put both edge lines in under stress and the edge face itself. And so we've kind of combined all those together, and it's like, well, we don't know whether it was the edge line that caused the fracture. We don't know if it was the actual edge face. And you can say, well, we could go back and look at the fracture origin. We can identify that. And I says, that's true, but wouldn't it be nice if we could just isolate the edge lines in of themselves to where we're just putting that in tension? So what we're going to do is tilt the standard, or the sample, a little bit at a slight angle to where, and if we go back to kind of our solid mechanics, we can come up with this first equation for combining both axes of bending into that. And we can come up with an angle based on our sample size to where we're going to put the one edge in complete, in this case, tension is what we're interested in, whereas the accompanying edge of that same edge face is going to be along the neutral axis, which means that there shouldn't be any stress or very minimal stress on that other edge. So in this case, we've basically isolated one edge. And so some of you are immediately going to say, well, aren't you going to have some lateral torsional buckling going on, or at least some lateral torsional bending? And that is true, but we're going to select our sample size to limit that effect, because remember, we don't have this, the glass isn't going to deflect a whole lot before it fails. And so as long as we've kind of handled our geometry appropriately, we don't get a lot of lateral movement out of the sample. So again, we're going back to a basic 4-point bending test, and kind of give you a picture of the actual test sample. So this one is currently very small, all right? So our sample is 6 inches long, and we're holding it at an angle of 7 degrees for our angled tests. And what we're able to do is distinguish between what was the cut edge, you know, where the tooled edge was, and the other edge as the sample breaks, and see, can we actually see if there's a difference between the tool side and the untool side. And other researchers have shown that there is indeed a difference through other means. And so our actual final geometry is going to be basically 150 mils long, about 25.5 mils tall, and a thickness in this case of about 3 mils. Okay, so again, a small sample. And this is just a proof of concept piece that we're trying to explore. Can we replicate some work that was done back in the 80s, and then can we scale this up, as hopefully where we're going over this summer is to get a bigger test rig and use bigger samples. All right, so having that been said, we're going to do 50 of the scored, we're going to do 50 specimens with the other edge, and we're going to do 32 of the standing, you know, just vertical, and we're going to see how does that fracture data, or how does that failure data compare to each other. All right, so I'm not going to, all right, so before we do that, one of the key things that we know is that when we propagate that crack until it becomes a critical flaw that actually initiates fracture, there is a time element to that, okay? So if I apply the same load very short versus over a long period of time, I'm going to get a different fracture or different break time or break magnitude, or fracture failure load magnitude. That's what I'm trying to say. So for us to set a statistics against that, it's convenient to take whatever it broke at and bring them all back to some common time. All right, so what we're going to take here is we're going to have some load regime, and this is just a kind of a theoretical one. It's not an actual one for this test. But whatever it is, you know, we're ideally to have some ramping load, but that's not always the case. It's certainly not the case when you use full scale. And we want to bring this back to some common time, and so we're just going to use this integration technique to kind of recenter it, normalize our duration, in this case to 3 seconds. We can make it whatever duration we want it to be, as long as when we use it later on our glass failure prediction model, we note that those parameters that we've created with this method are anchored to that duration, and we correct duration for other things. And you see this in the analytical method of E1300R rating, where you have a similar equation, but it has a 60 on the bottom of it, because those glass failure prediction model, or the surface flaw parameters, were based on a 60-second duration back in when those were created. All right, so what did we come up with? Well, so for the scored edge line, we came up with a series, and the magnitudes in and of themselves aren't super important, but the relationship of the magnitudes. So let's just keep in mind in this case that around 520 newtons was the failure load. And again, these are pretty small samples. And we also note that there wasn't a huge spread here. So our coefficient of variation, fairly small. And then we did the straight up and down. And in this case, we got about 670 newtons. So that was an increase. Okay, so if we based all of our fracture data, or our strength data, based on the standing seam, then this would indicate that the samples were actually stronger than they would have been if we were just isolating that one edge. And remember, for structural glazing scenarios, we may not always have perpendicular loads passing through our elements, right? We need to be able to handle these loads and stresses coming from different directions and different orientations. All right, so we go the other way, and so we look at, this is what we call the other edge. This is just the edge that wasn't cut by the tool. And we see that now we're up to 770. So we've seen that basically, if we look at the tool side, was the weakest, and we can kind of summarize them here. And the top one was the original failure data, and then the bottom one is going to be our corrected failure data. So this slide is just to kind of give you a sense of how much effect did normalizing to 3 seconds adjust our magnitudes. It also kind of changed our coefficient of variation a little bit by doing that. Okay, so these are two places. Not huge changes, but we all know, or at least we have now, this common time element to our failure loads. Again, notice that our means propagate pretty nicely. And it's worth noting, the ones with the asterisks, is that we've subtracted 4 specimens out of those 50 that we felt like were outliers. Okay, and all right, so on our way to establishing our glass failure prediction model parameters that we need, that we talked about, we typically take a ranked probability for our actual data, and then we start fitting curves to it. Again, we're using that modified strength risk function with the Weibull distribution to account for the length. Okay. Now in this case, because we have 4-point bending, the length factor kind of drops out. But when we go on to other scenarios, we can address situations to where the stresses are not constant within our region or across the edge. Okay. Now, one thing that we noted is that the bottom of our tail here didn't seem to fit very well. Okay. And as we know, for a Weibull distribution, the whole point is looking at kind of what's going on that left side of the tail, right? So we would prefer that if we were going to match something, that the tail should match, right? And so it's like, well, what can we do about that? So we can linearize our data, and we start seeing that there's quite a bit difference in that tail and this is for the actual cut edge is what the SEL series is. So this is the data that we feel like this is the weakest, and is this, we want to make sure that we capture this accurately. And so we have this big bend. If we notice the red and blue series for the standing and the other seam, those seem to still fit reasonably well with our distribution. And so this is where we can come in to take what we call a bilinear distribution, to where we kind of break up the sample set into 2 different distributions. And now we have one that clearly fits the upper trend, and then we have one that fits better the lower trend because there's this kind of this kink in our data. And so then we start asking ourselves, well, what is this kink actually in reality? Is this that we're seeing two different failure mechanisms that are happening on the edge? And if so, what are those? Or is it that our sample set, even though we used 50, which is a reasonable amount, is it just that we don't have a significant enough sample set to actually see that those ones on the lower kink are actually just our smaller values, and that if we had sufficient amount of specimens broken, we would see this straighten out, and this is just an artifact of ranking such a short number of specimens. Okay, so that's a question that we're still addressing. But if we go ahead and just kind of magnify this, remember we said that ASTM E1300 is built on this threshold of 8 in 1,000 or 0.008, and what we notice here is that the solid black line was that original cut edge distribution, but we said, well, that didn't really fit well at the bottom. And if we use the secondary, the bifit, then we come up with this dashed black line. And now that data is telling us that our cut edge is actually stronger at this lower probability than our the one that was the highest, which was the other edge. And so the question is, does that actually make sense? And so in this case, I think that we're probably over-predicting the strength by using that other fit, because rationally it shouldn't match. So the question is, how do we figure that out, okay? So first, the angle test does a nice job of being able to distinguish the different kind of areas or kind of components of the edge that we can have a failure at. And so we can quantify those differences pretty nicely. And we also had what we kind of would expected is that we have a weak edge line. We have something in the middle that's the kind of the combination of both, right? Kind of the average, if you will. That's the standing. And then we have our best case, which was in this case the uncut edge, all right? And even though our bilinear Weibull distribution fit seemed to match our data better, I'm not convinced that it's really giving us, a good model at the end. So we're gonna explore this more with larger sample sizes as we move forward to figure out, are there two mechanisms that are actually causing our break and that's real? Or is this just, again, an artifact of our ranking and fitting our distribution? So that's something that I'm gonna work on. So our true motivation here is to expand this out to larger sample sizes, because then we can start doing thicker glass. We can start doing different edge treatment like polishing or chamfering or whatever other treatment we want to look at. And we can also look at heat-treated glass, okay? Because then we're able to go through and actually look at each step of the way what's going on with our edges, and then we would come up with potentially a set of glass failure prediction parameters for each type of glass or each type of edge and whatever combination we want. And then one could go in for a design point of view and say, okay, I need these parameters for this kind of edge. Just as you would do if I have this kind of polished edge, I might have a different maximum stress that I'm going to limit myself to. We're going to take this a little bit further and put it into the glass failure prediction model. So this is kind of some preliminary work that we're looking at. We're in the process of finishing up our larger test frame to accommodate larger samples, and I will entertain some comments if anybody has any questions or things you'd like to add. Richard, I guess.
It's interesting work and series of questions.
Yep.
So first of all, thank you, Stephen, for the presentation.
Yep.
Now it comes to questions.
All right. Jump ahead.
Going back to some of the work that Leon Jacob did a long time ago, and was talking about there is a nature of a limit on the critical floor. I'm wondering whether in this situation you're seeing the evidence of the self-healing process and how long there was between when you cut the glass and when you tested it. And so you're almost getting a double distribution as you're seeing, one which is a distribution due to the cutting effect, which is introducing more flaws, and then you're seeing a self-healing process where you're coming back to it self-healing to a common point depending on how the edge was actually formed.
Okay, so I can expand a little bit on that. So this was cut at a local glass shop by hand, but they were actually fairly close in size. I was impressed that somebody by hand could do it that accurately. So to that point, they were tested within a week or two of when it was cut. And this is just using a regular kind of diamond wheel cutting tool. I think you bring up a good point there to where, and that's something we could do, is cut two different sets, set one aside, leave it untouched for a period of time, and then go back and see if there's a difference. Since they came from the same piece of glass, they were cut at the same time, and just see if there's a variation in that testing. So that's a good recommendation. For the annealed case, I think if we're going to heat treat it, then that becomes not a big issue. So yeah, we can definitely look at that.
More questions?
I have a question. Stephen, it sounds like you didn't always record whether you were cutting from the tin side or the air side. Is that right?
No, that was labeled. We knew, I think these were all cut on the air side, because I think we had made a comment here. Where did that go? Oh, yeah, that's the first one here. Scoring on the tin side and see if that makes a difference. But these were scored on the air side, because we took the little UV light over to the glass shop and checked which one he was cutting before he cut it, and then we kept track of that. Just when we marked the samples, they were all stacked and kept, so we knew which side was what.
There's one last question.
Okay. It was a very interesting work, in my opinion. Can you come back to the slide in which you show how the data are fitted by the bilinear distribution? Yeah. Have you made some consideration about the distribution of cracks or crack sizes? Because, just for explain why this question. Here we have a trend that is similar to what expecting, that what is exhibited by surface strength. Because even for surface strength, two-parameter Weibull distribution goes to zero too fast.
Right. And
say we have studied a bit this problem. We proposed the left truncated for surface cracks. But the problem of the edge is that the defective scenario is much more complex than for surface strengths. And the Weibull distribution comes from a Pareto function for crack sizes. I think that for future work to make some consideration on the crack distribution, even though I know that it's much complex for the edge strength, would be useful to understand why we look at this trend, because it would be even that there are not two mechanisms, only one mechanism, but there's something in the crack size distribution that say to us why we have this kink.
Right. And that's a good point. And I kind of have a conflict with it, just, do we drive that far into it because we think about production level? That's, we're not probably ever going to check that. And so so it's a point well taken. We haven't jumped in that far with it yet. So I appreciate the comment.
Thank you.
Thank you.
Hi there. Did you like what you just saw? If you did, why don't you like the video, drop us a comment below, and share the video as well, since GPD is all about sharing. And to receive more videos in future, subscribe to this channel and don't forget to click the bell icon. Ciao.